Welcome back. This is an Aleks training video on calculating the pH of a weak base solution. When you have a weak base, it doesn't dissociate completely. And a base, remember, is anything that accepts a proton. So in the case of this base, this is morpholine. Morpholine, never heard of morpholine. But morpholine is a weak base. And as such, if you put it in water, the water is going to act as an acid. The water will break up because there's a hydrogen here to give. The water will break up. And then this H from the water will come off, and you'll end up with an OH left over. That's an OH from the water. And then this H will join with this base to become its conjugate acid. So you can see that here we had one H. Here's the second H. It comes along. You're going to end up with two H's. And remember, it's a positive, so you'll end up with a positive. So this is the conjugate acid of this base. Morpholine is a base. So it's going to receive a proton from the water. So because of that, you have no H3O. You have nothing. You don't have an acid here. You have a base. So when you find out a base, you want the concentration of the OH, because that's the only thing you have. We're trying to find the pH, but we don't have a hydronium ion. And remember, if you have the concentration of the hydronium, it's the negative log of that concentration, and then you have the pH. You're asked to find the pH of a solution that's not acidic. All you have is the base. So we're going to find the concentration of the hydroxide, and then remember that water, which is 1.01 times 10 to the negative 14, will always be the product of the concentration of hydroxide plus the concentration of the hydronium, always. So if I have the concentration of this, I can divide it into 1.01 times 10 to the negative 14 and get the concentration of hydronium. Once I have that, it's the negative log, and that's the pH. You're given the base constant, okay, the product or the ion dissociation protonation constant, the base constant, and because of that, I need these numbers. So that I can find out what the concentration of the hydroxide is at equilibrium. Once I know what it is at equilibrium, then I can find the hydroxide and then find the pH from there. So this requires, since this is the beginning of this problem is not equilibrium, I have to have an ICE table. ICE, remember, stands for initial. So you're going to give the molarities what you know at the beginning. The change, all right, the change in this case is going to be, I want the concentration of the OH, and then the equilibrium is the sum of the two. So let's see what we got. What do we know? The only thing that we're given is that 0.27 molar is the molarity of the morpholine. Okay, so let me write that in. This is going to be 0.27 molar. Okay, what else do I know? I know at the beginning, I've only got this. Water is a liquid, so it's not going to be considered at all. Then I've got the conjugate acid of the morpholine and then the hydroxide. Well, at the beginning, I only have this shoved in water. So there is no concentration of this, and there's no concentration at this at the beginning. So this is pretty simple. At the very beginning, you're simply going to say that that's 0 and that this is 0. All right, so far, so good. Now, the change. What do we want to know? We want this. We want this so that we can find this and then get the pH. That means that this is going to be my X. When I have the concentration of hydroxide, then I can do something with it and get what I want. So this is my X. So I'm going to go back to here and say the concentration of hydroxide is going to be X. And now This is a balanced equation. I balanced this. It just happens to be that it's a 1 to 1 to 1 to 1 relationship. Okay, so there's no coefficients. Remember that this expression here, the case of B expression, is this first guy's concentration taken to the power of its coefficient. Well, that's a 1, so this is going to be power of 1. I'm sorry, this one, the power of 1. This is hydroxide taken, there's 1 here, so it's the power of 1, and this guy is 1, so this is the power of 1. So because of this, as soon as I get X, I know that X is hydroxide. This is a 1-to-1 relationship with this guy. This is also X. Because if this is X, this is going to be X. This, since it's 1-to-1, and since this is 1-to-1, this is also X, but it's on the other side of the arrow, so this is going to be negative X. So going back, this will be X because it's a 1-to-1 relationship, and then this is negative X because it's a 1-to-1 relationship, but it's on the other side. So it has to be negative to whatever X you have. The equilibrium then is going to be the sum of these two boxes. So if you have negative 27, so we have 0.27 minus X, that'll be your equilibrium for the C4H8. And then this guy is just going to be 0 plus X, so it's going to be X. And this guy is going to be 0 plus X, so this is X. Right? So now I need to know what X is. The way I can solve for it is to go back to my expression here. K sub B equals these concentrations. And I know what these are now. This is going to be X, this is going to be X, and this is going to be 0.27 minus X equals K sub B. And I know K sub B is 2.14 times 10 to the negative 6. So let me fill that in down here. I've got K sub B, which is 2.14 times 10 to the negative 6. I have the top, which is the first one I have as X. The second one I have also as X. And the third, in the bottom, I have 0.27 minus X. Now, when I see this, I instantly get scared because what this means is if I were to multiply 0.27 minus X to the top, I would have X squared on one side and an X on the other, and the only way that I could answer this is by the quadratic formula. I don't want to do the quadratic formula. It takes me 15 minutes to do it, and I don't even know if I can get it right then. So I'm going to ask myself a question. This is a weak base. A weak base means that most of the stuff that you put in the water is going to stay in the entire molecule. It's not going to break apart. And so what is it going to be? This X is going to be very, very little. My guess is that it's going to be, I don't know, less than a hundredth, maybe, less than a penny worth out of $1. So that means that it would round off anyway. Even if I went to all the trouble of finding this X and dividing by it, this part would only just divide off anyway. So I'm going to fudge this. I'm going to take my eraser and I'm going to erase just the minus X there. And by doing that, I now can take the 0.27, bring it to the top, and I have 0.27 times 2.14 times 10 to the minus 6 equals X squared. X is going to be equal to the square root of 0.27 times 2.14 times 10 to the negative 6. And X is going to be equal to 7.601-ish times 10 to the minus 4. Okay, you can see this. This means it's 0.0007 it's so tiny that this is just going to be rounded off anyway. So that's why I was able to erase that negative x and not have to go through all that horrible math. Okay, so because you'll get the same answer anyway, either way you're going to do it when this rounds away. So what did we find? Okay, we found that x equals 7.6 times 0.01 times 10 to the negative 4. Well, what is x? X is the hydroxide concentration. That's what this is. This is what the 7.04, 7.601 is the hydroxide. Well, I can come back to this, put this number in. So let's fill in what we know. This number will always be the same. This will be 1.01 times 10 to the minus 14. That's K sub W. That's in a data table. You can look that up. It never changes. This, the hydroxide, is what we just found. This is 7.601 times 10 to the minus 4. So I'm just going to divide these two. I'm going to take 1.01 times 10 to the negative 14 divided by 7.601 times 10 to the negative 4. And you'll get the acid concentration because that's how you're going to find your pH. So this is going to be 1.329 ... times 10 to the minus 11. Okay, so that is the concentration of hydronium. I'm one step away from getting the pH because remember that the pH is going to equal the negative logarithm of the concentration of hydronium. So once you have a concentration of hydronium, you've got the pH. We've got 10.8765 ... Now we need to find the pH to 1 decimal place because that's what it says in the directions. Round your answer to 1 decimal place. That means it has to be the 8, and the 8 will go up to the 9, and you'll have the pH equals 10.9. And there you go.